Hi, my name is Stephen Rosenberg, and I'm giving a presentation on predictive analysis for migration schedulers. This presentation will explore the possibility of using predictive analysis in order to predict when some processes will complete in order to start the migration of mission-critical or high-priority processes early, when the soon-to-be freed resources will provide performance improvements within a distributed system, such as within a data center or possibly across data centers. Early migration may also include fault-tolerance solutions, of which there is growing interest. The ability to migrate processes, whether they are VMs, worker nodes, managed by orchestration applications, pods, containers, or other types of processes, provides for many options in conjunction with predictive analysis, which we shall discuss shortly. So the topics that we can discuss are load balancing solutions, fault tolerance, scheduling, types of live migration, and predictive analysis. So this is a load balancing example, and you can see you have a load balancer, and you can see that process one, which could be VMs, it could be pods, as I said, worker nodes, that runs on host one, the process two is on host 2, 3 on 3, and then because we only have 3 hosts, process 4 goes to host 1, and that's called a round-robin approach, and that gives us proper load balancing. So for load balancing, we can have priority based upon urgency. We can define processes as urgent priority, high priority, neutral priority, low priority, and no priority. So if we want to consider, for example, giving more resources to urgent or high priority processes, we can actually bring down the no priority and low priority processes, which is one method of keeping the system resilient and giving priority to processes that need it. Fault tolerance. Well, what can go wrong? Well, there are many opportunities for failures. Network element failures, hardware resource failures, OS bias kernel failures, and process failures. So some solutions currently are high availability where you have redundancy. And you can see here you have a host 1, which is active. The host 2 is passive. You have storage hosts which are redundant. You have redundant connections, and this leads to not only higher cost, but it also leads to higher latency because, say, process 2 has to wait until he actually receives an indicator that host 1 is no longer really active. So we would like to find better solutions. So here's an example of scheduling to dispatch various processes. So you see here you have a process 8 and a process 9. They could be anything. And basically there's an open slot on host 2 and an open slot on host 3. So 8 could be scheduled to launch or migrate, if you will, to host 2, and process 9 could be scheduled to run on host 3. But what if 8 needs 2 slots? Well, then the problem is that it has to wait until there's a free slot either on host 2, host 3, or possibly 2 processes coming down on host 1. But if you have a more intelligent solution, you can move process 5 on host 2 to host 3 and migrate that, and then you can launch process 8 onto host 2. But if you can predict that process 5 is going to exit within the time it takes to launch, or if you will, migrate process 8, you can start the launching or migration of process 8 at the same time launch or migrate process 9 to host 3, And once the migrations are complete, host 5 will no longer run. Host 8 will be running on, process 8 will be running on host 2, and process 9 will be running on host 3, and that's a more intelligent solution. So scheduling is the ability to launch processes based upon needed resources. Monitoring the amount of resources each process utilizes is one aspect that we can consider. The types of launching or migration scenarios, we can consider the initial launching, which we discussed, migration for maintenance if a host needs to be brought down for hardware upgrades. You can migrate the processes from one host to another. There's rebalancing opportunities, migrating to another host in order to have a better load balancing. And for fault recovery, migrating to mitigate the system process failures. So policy units that we need to consider, attributes of scheduling migrations. You have filtering. If a process needs a certain piece of hardware, only those hosts that have that hardware will be considered, and hosts that do not have that will be filtered. Then you weigh the host candidates via scoring based upon if it's the balancing, if it's even distribution. The hosts with the most free resources will have a higher score. If it's power saving, then those hosts that use the least amount of energy will have higher scoring. You can consider prioritization, which we discussed, affinity, CPU pneumo-pinning for optimal performances. There's many criteria for that. So solutions for applying predictive analysis, you can have live migration, load balancing, fault recovery, minimizing live migration pausing. We can consider all of those with predictive analysis. Redundancy, that covers distribution of processes running simultaneously, and it applies to fault recovery, as we discussed. And for much more reliable fault tolerance, you could actually combine the two. So live migration. The idea of live migration is to move a process from a source host to a destination host. And the idea is that the process will continue to run on the source host while you set up the destination host in order to reduce the amount of downtime and latency. So the things to consider when setting up the destination host is the network connectivity, the remote disk availability, migrating the data from the local host on the destination, on the source, and moving that data to the destination, copying memory states in phases. That includes moving all of the memory that the process is using from the source to the destination. Then while the process is still running on the source, to remove the deltas, the current differences of the memory, until you calculate the minimum pause time that the process can be brought down to copy over the differences. Then you copy over the CPU state. And again, the goal is to limit the pausing of the process. And then you can restart the process on the destination host once you've stopped the process on the source host. And then you can clean up all the data on the source host. So we can illustrate that through these transitions. Currently, the process is running on the source. We set up or synchronize the disk, and we start the memory transfer. We estimate the minimum downtime while we continue the memory transfer and the deltas that are accumulating. Once we reach the minimum downtime, we pause the process on the source, we activate the network, we complete the memory transfers, we then run the process on the destination, and then we do the cleanup on the source. So for live migration from host 1 to host 2 transitioning, considering the local disk data on host 1, you can see that the guest process already migrated to host 2. It requests the data from the controller on host 2, which communicates with the controller on host 1. It accesses the storage that still hasn't migrated yet, so that the process can use it currently. And at the same time, data is continually being transferred from host 1 to host 2 via the controllers until all the data is copied to host 2, in which case you no longer need the connection. So predictive analysis topics for discussion. We can predict future occurrences via analysis of past performance, and that's the concept. Techniques for predictive analysis will be discussed, process for developing a predictive model, types of predictive models with examples, and how we can apply that to scheduling. So a predictive analytics model, you first start with the historical data. And from that, you create a training set. You develop an algorithm, and the algorithm runs and creates what's called a model. You then use a test set in order to test the model, and you look at the results. And you compare the results to the expected results. You calculate the percentage of error. You'll then modify the algorithm, and you'll do the process over again until the percentage of error is at a lowest threshold, and that's acceptable. And that's called machine learning. So there are many techniques for predictive analysis. I won't cover them all, obviously, but the idea is that you shouldn't be a solution looking for a problem. You should define the problem first, and then choose the best solution for your problem. So the process for developing a predictive model, again, we define the project, we collect the data, we analyze the data, we validate the data, we create a model, or we deploy that model, we monitor the model, we calculate the percentage of error between what we expected, we then redefine the project, and we run it over again. So that's a cyclical learning. So the types of predictive models with examples. Support vector machine models or classification models to predict a category. Examples can be stock prices increase or decrease. It can be yes or no. Predictive quantity regression. Examples could be predicting a person's age based upon height, weight, health, and other factors. Detecting an anomaly, you're comparing normal behavior versus exceptions, such as money withdrawal anomalies. If money is missing from your bank account, obviously that's something to be concerned about. Clustering, discover structure in unexplored data. Examples such as finding groups of customers within similar behavior, giving a large database of customers containing their demographics and past buying records. That is other techniques that we can use in creating predictive models. Applying predictive analysis and analytics to schedulers, the criteria for data, processing time iterations, and we should adjust for resource capacity and priority to get better results. Percentage of resources used, adjusting the data for capacity and priority, adjusting for anomalies when calculating averages, which we'll discuss later. The ideas, certain selective techniques that apply to other scheduling applications can be applied to our types of scheduling applications. They could be machine learning and advanced mathematical models. They could be combining regression-like modeling and functional approximation using the sum of exponential functions to produce probability estimates. And we can take examples from other areas and apply them here as applicable. So this is a predictive analysis architecture. The historian can collect the data from the scheduling that interfaces with the hosts. It can keep track of various types of data and parameters, the CPU, memory, storage, networking usage, and the scoring for the migrations. The predictor can then read from the historian, create predictions, and then communicate with the scheduler, such as to tell it to perform a live migration. Tracking historical data. The time each process starts and terminates is important data for us to collect for this type of application. The resources used by each process, the time each process uses to migrate, the time and iterations that memory or disk transfers occur per size. These are all the types of data that we would consider collecting. Considerations based upon analysis. We need to consider if early migration can proceed, when early migration shall start, and error correction and anomaly detection for accurate results. Techniques that we can use for anomaly error calculation methods. Statistical, where we can calculate the percentage of error from the mean and eliminate results outside of the threshold in order to make sure that our analysis is more accurate. Signal processing techniques, if we want to be more fancy, creating smoothing filters to eliminate glitches, and machine learning, analysis of patterns and categorization between normal and out of range results. These can all be used in order to eliminate the outliers and to only consider the actual valid data. Thank you very much. I'm open to any questions. Thank you. Hi. Okay, so I see there's a few questions. Let me go through them. Someone asked if it's possible to have slides. Yes, here's my email address. You can ping me and send me your any questions you would like offline, and I can actually send you the slides and share it with you. Some people ask, how do you plan in improving accuracy of short-term non-stationary time series analysis, which is typical of network traffic over day week due to sessionality of data? Did you consider using auto-regressive models to perform the forecasting, such as ARIMA models? So first of all, this is a work in progress. It hasn't actually seen implementation. It went through some testing. As I said, we look for the best solutions, and time series analysis may not be the first phase. First phase may, for some of the applications, such as fault tolerance, might actually just be a simple rule-based type algorithm. As far as accuracy, I think I did explain that we do want to filter out outliers in order to get more accurate results. Another question from, that was from, Matteo Setenvini. I hope I pronounced that right. And he had a second question. Do you use ROC, receive operation characteristic curves, to evaluate the quality of the prediction when using SVMs or other binary predictive models? Well, we are open to suggestions, and I can look through a lot of that. But as I said, I have considered filtering of outliers in order to get better predictions and to be able to quantify that the calculations will be accurate. David Stirs said, thanks for it. It was interesting. Are there any known implementations out there? As I said, this is a work in progress. Anyone who is interested in it, would like to be involved in it, they can ping me. This will be an open source project, and we welcome anyone that's interested and willing to participate. Mithilesh Kumar, are you planning for any hands-on sessions? Well, that's a good possibility. Currently, we're considering starting the project and moving it forward. And once we have something to demo, it would be a good idea to also demo it, and that would be a future consideration. Amr Mukhtar said, how do you decide on which variables to use in learning the prediction model? Well, as I said, we need to consider the many different indicators. If we're talking about what I call early migration, the variables were discussed. We need to be able to learn how long processes run. Some processes will be more predictable than others. It depends upon dependencies. When there are dependencies, such as database, and as the tables increase, obviously those dependencies will affect performance. And we can do calculations to kind of anticipate that. And we can categorize processes based upon the level of prediction of how easily or how hard it is to predict. For fault tolerance, we have various types of indicators that we can use. One possibility is degradation of performance, not just in the networking area, as most load balancers consider, but also the CPU percentage and the memory usage, as well as the storage usage. And all of those can be considered for migrating processes. That also not only gives a better load balancer, it can also, if the degradation of performance is due to a fault, something component is failing, then you also have a fault tolerance system. So Shantanu Deshpande, he asked, is there a practical implementation of the discussed ML approaches? Well, you always want to choose the best solution for the problem at hand. So as I said, for some scenarios, simple rule-based can work. And then when you want some more robust approach, you can also choose different machine learning approaches. It could be Lambstar or neural network type of approaches, and you need to balance which is the right ones. And as I said, you could use existing scheduling algorithms that are used for human scheduling their processes to also apply some of that to these types of problems as well. So it's a matter of mixing and matching. Xavier Sierra said, what data do you commonly collect in order to predict resource consumption? As I said, it could be CPU usage or CPU percentages. It could be memory and storage. It could be networking. It can consider not only the percentage of usage, but the size. For example, storage, it would not only be the throughput and considering the latency, but also the amount of disk space that's left. So I already covered some of that. I hope that's more detailed. Disha Agawal, is there any online data sets for this experiment? The beauty of this is that you can actually simulate degradation of performance with stress tools and generate the data. And then once you actually generate the data, then you have the data. So unlike a lot of projects where you first have to collect the data and then analyze it, this project you can actually generate the scenarios and then have the learning from the data that you've generated. So this is the unique ideas of this particular project. So Herman Gonzalez wrote, is there a pre-made tool in order to help with the predictions? What tools do you use? Well, again, it is a work in progress. And as I said, the whole idea of this project would be you start small and then you grow big. So we could start, as I say, with fault tolerance. We could start with a rules-based type algorithm. We could then develop a machine learning and then choose the tools. And then the machine learning can eventually, once we're confident, actually write the rules on the fly. So I have many ideas for moving this project forward. If the people are interested, please ping me, send me, contact me, and we can discuss any contributions that you can give to the project, and any contributions would be greatly appreciated. Thank you. If there's any other questions, I think I covered them all. Yes. Okay. Yes, there's a second page. David Stirs, would you see implementations within a Kubernetes SIG? Which ones? Also, I understood it has to be combined with a custom scheduler or a normal one. Well, as I said at the beginning, for Kubernetes, worker nodes are usually VMs. And that's a very good candidate. We do have systems that perform live migrations. Red Hat has OpenStack. There's Rev, and there are many solutions for migrating VMs. And there are also experimentations for migrating pods and even containers. So that's where it can really be applied to Kubernetes. As well. Xavier Sierra, have you considered an automatic training approach like AutoML, TPOT, etc.? We're open to all kinds of ideas, and we can certainly consider those options as well. Faizig Gavimi, do you think that a deep learning method can predict anomaly in the cloud network and detect anomalies for different types of applications? Yes, I do. If you have the proper models, you can certainly predict when there's anomaly in the cloud network, so long as there's consistent patterns. And that's the whole idea, is to be able to detect the consistent patterns, to be able to train the application in order to differentiate between the normal operation and the anomalies. So yes, I believe so. Himanshu Srivastava, can you use this EXP for non-time series data like application logs? Yes, you can actually, the Red Hat has a product called Insights, and we actually read from the logs. And then when an event happens, we can then run automation in order to fix it. If you can predict beforehand these kind of issues, then we go one step beyond Insights. And yes, definitely collecting data from the application logs as well is a good approach for learning from failures in the history of the system. And this way you can then detect and mitigate those sequences of events that led to those failures, and hopefully mitigate those failures beforehand such as with a live migration, which is the core aspect of this idea. So the Getty, what kind of networking data is being looked at, throughput or latency? Well, I would say all of the above, including the amount of resources that are available as opposed to amount of resources are being used. So I think I discussed that before. Disha Agarwal, can you name a few simulation software, perhaps like GNS3? Well, there are many software solutions for creating stress. There are stress testing applications and things of that nature so that you can generate the data, and then from the data you can also from that data that you generate, you can then also use that data in order to train. And I'm sure there's many other software applications out there for simulating. Okay. I hope that was helpful. I don't see any other questions. Okay. Also, I'm told that I can upload my slides into the scheduler, and then all the attendees can download them there. So I'll also consider that as well. Okay, so if there isn't anything else, if there's any other questions, thank you very much for joining, and I hope it was informative. And as I said, if anyone wants to get involved, please contact me, and we can discuss. There's so many good ideas in these questions, so I'll certainly consider a lot of it. Thank you.